Today I discuss on important topics related to linear algebra, especially adjoint of a linear operator. Okay, then we also here discuss adjoint of a linear operator. Okay, we know about that, but here we also discuss in proper way. We know about linear operator. Which one is linear operator? That means satisfies some conditions, and obviously one functions from one vector space to vector space is called linear operator. Okay, then we're also going to discussion here a linear operator on a vector space V. Okay, here is called adjoint of T, whose matrix representation with respect to orthonormal basis beta is T beta star. Okay, so we write it in this way. That means we define a linear operator on V is called adjoint of T. Okay, we define a linear operator. Okay, we define a linear operator. Okay, we define a linear operator on V called the adjoint of T, called the adjoint of T. Okay, whose matrix representation whose matrix representation okay, with respect to any orthonormal basis beta, with respect to any orthonormal basis beta. Okay, for V is here T with respect to beta star. Okay, then we're also going to discussion here. Okay, what that means, let VVN inner product space VVN inner product space, and let Y belongs to V, Okay, the function G here V to F defined by okay, what defined by Gx equal to inner product of xy. Okay, is clearly linear, okay, and now every linear transformation, okay, from V to F, obviously we define this form. Okay, so what happened, we also define one functions here Gx equal to inner product of xy. Okay, inner product of xy be linear. Okay, now we also discuss here, if V is finite dimensional, then every linear transformations from V into F is of this form. Okay, if V finite dimensional, if V be finite dimensional, if V be finite dimensional, then every linear transformation, linear transformation every linear transformations. Okay, every linear transformations from V into F, from V into F, okay, is of this form, is of this form. Okay, now we erase that portion and going to further discussion on theorem. Okay, also known about that this adjoint of linear operator. Okay, obviously that means this one gives one matrix T with respect to orthonormal basis beta, T matrices with respect to orthonormal basis beta, and then this adjoint. Okay, so now we erase that portion and going to further discussion of that. Okay, now we discuss one theorem related to that. Okay, here we write theorem, and let V be a finite dimensional inner product space. Let V be a finite dimensional inner product space. Finite dimensional inner product space. Okay, over F, and let G V to F, and let G V to F be a linear transformation. Be a linear transformation. Okay, then there exists a unique vector. There exists a unique vector. There exists a unique vector y belongs to V. Okay, such that Gx equal to inner product of xy. Okay, for all x belongs to V. Then what happened? That there exists a unique vector y belongs to V. Okay, such that Gx equal to inner product of xy. Understood? Now we're going to proof of that. That means what this theorem says. We also just talk about in short one linear transformations, and obviously one linear transformations represent one inner product. Okay, that means here is this value linear transformation G taken some value x. Okay, that means then Gx. Okay, then this Gx equal to some functional value since Gv to F and x belongs to V. So this Gx represent this the Gx some functional value obviously represented by one inner product value, and obviously this x inner product with one vector of V. Okay, that means vector of some domain of Z, vector coming from this domain of Z with inner product of x equal to the functional value Gx. Okay, this one is an crucial theorem, I think. Obviously we also discuss later. Today now we proof of that. Okay, here we write proof. So what is here? Let beta equal to v1 v2 vn. Okay, then Vn be an orthonormal basis, orthonormal basis for V. Understood? Then let y equal to summation I equal to 1 to n. Okay, G of Vi, and here conjugate Vi. Understood? Now define h of v to f by hx equal to inner product of xy. Okay, which is clearly linear, which is clearly linear, which is clearly linear. Understood? Which is clearly linear. Okay, now what happened is here. Furthermore, for 1 less than equal to j less than equal to n, we have, okay, we have what? HVJ equal to okay, inner product of VJY. Okay, inner product of VJY equal to inner product of VJ, here I equal to 1 to n. Okay, G of VI conjugate VI. Understood? Then this one equal to what? We erase our portion. So what we do? We take beta v1, v2, vn, pn orthonormal basis for v and let y equal to this one. Understood? Y equal to this one. Okay, that means some linear combinations of p I, that means coming from this basis, orthonormal basis beta. So we now also discuss here, define h v to f, hx equal to this one, this inner product xy, which is clearly linear. This one's happened. Now furthermore we also discuss h of vj equal to this one and this one equal to, we put y here. Then what happened? Wait, now erase that portion and further progress. Now so here what we write in this way, we also discuss this one equal to I equal to 1 to n. Okay, g of vi conjugate, whole conjugate. Okay, then what happened here? vi. Understood? vj vi. Okay, then what happened? This one equal to I equal to 1 to n. Okay, g of vi, here del of ji. Understood? Del of ji equal to what? T equal to g of vj. Understood? Then what happened? Then since g and h, okay, both agree on beta, okay, we have that g equal to h. Understood? Then what happened? Then we have to show to a y be unique. Okay, to show that y is unique. Okay, to show that y is unique, here suppose that what happened? Gx equal to x y dash for all x. Okay, then what happened? Then inner product of xy equal to inner product of x y dash, okay, for all x. Okay, then what happened? Then we have what? We have y equal to y dash. How this one happened? Also see it. That means in this way, xy difference xy dash equal to 0. This implies that what? This implies that x y difference y dash equal to 0 equal to 0 sorry x 0. Okay, then what happened? Y equal to y dash. Understood? We get this one, not a problem at all. Too easily we get this one. Understood? Then what happened now? We're also going to one example related to that topic. So okay, so now we erase that portion and going to discuss one example of that. Here define g r square to r, okay, by here g of a1 a2 equal to 2a1 plus a2. Okay, clearly g is a linear transformation. Clearly g is a linear transformations. Okay, then what happened here? Let beta equal to e1 e2 and let y equal to ge1 here e1 plus ge2 here e2. Okay, then what happened is here ge1 equal to 2. Okay, 1 0, that means 2 here, 2e1 plus ge2 equal to 0 1 here 1 e2. Understood? Then what happened is here, that means 2 1. Understood? So y equal to what? 2 1. Okay, then g of a1 a2 equal to what? G of a1 equal to what? Here a1 a2 here 2 1. Okay, then 2a1 plus a2. Understood? Now we also write it here in some theorem. Okay, we write again one theorem. Let V be finite dimensional inner product space. Let V be finite dimensional inner product space. Okay, and let T be a linear operator on V. T be a linear operator on V. Then there exists a unique function, okay, T star here V to V, such that what? Such that here inner product of Txy equal to here inner product of x T star y. Okay, for all xy belongs to V. Okay, furthermore T star is linear. Furthermore T star is linear. Okay, understood? Now we erase that portion and going to further discussion on theorem. Here what we write, V be a finite dimensional energy product space. Finite dimensional means what? Means dimension of V is less than plus infinity. Okay, that means simple, the basis contains finite elements. Okay, then again, here inner product space means we know about that one space, vector space with some inner product defined on this space, and then this one are that means having some properties and satisfies those properties. Then this one is called inner product space. Then T be a linear operator. We know about that linear operator is that some property additivity and some homogeneity, okay, or scalar multiplicativity. This one satisfied, I think. Then what happened here, that means there exists unique function T star. This one satisfied. That means some inner product of Txy equal to x T star y. Okay, we have one unique function T star. We get this one satisfied. And obviously furthermore T star be linear. Okay, that means well, so now yes our portion. Then we'll be going to discussion of that. Okay. We write here proof. We write here proof. Okay. Let y belongs to V. Let y belongs to V and define GV to F by what? Gx equal to okay Txy, inner product of this for all x belongs to V. Understood? Then what happened? We first show that G be linear. We first show that G be linear. Okay. Then what happened is here. We also take let x1, x2 belongs to here V and C belongs to F. Then what happened? Then G of Cx1 plus x2 equal to what? Inner product of T Cx1 plus x2 and here y. Okay. Then this one equal to what? Ctx1 plus tx2 y, inner product of this. Then this one equal to what? Ctx1 y plus tx2 y. Okay. Then what happened? Cgx1 plus gx2. Understood? Then what happened? Hence G of Cx1 plus x2 equal to C of Gx1 plus Gx2. Then G be linear. Okay, not a problem at all. We prove this one. G be linear. Okay. Now we're going to discussion of another portions. We apply to previous theorem. Okay, we use previous theorem. Okay, and to obtain a unique vector y dash belongs to V such that Gx equal to Xy dash, inner product of this, that is inner product of Txy equal to x y dash. Okay, for all x belongs to V. For all x belongs to V. Okay, then what happened? Then defining this star. Okay, defining this star for this star V to V, V to V by this star y equal to y dash. Okay, we have what? We erase our portion and going to further discussion of that. Okay, so that means we also see here what we have. We have x txy equal to x t star y. Understood? Not a problem at all. That means txy xy dash equal to txy x t star y. Okay, then again we show that to show that this star be linear. Okay, we now show that this star be linear. Okay, that means this star is additive. Okay, and obviously scalar multiplicative. Okay, then what happened? Then we let here let y1 y2 belongs to V and C belongs to F. What happened? Then for any x belongs to V. Okay, we have what? It is this lower portion. We have here x t star c y1 plus y2 equal to tx. Okay, cy1 plus y2. Okay, then what happen is here tx cy1 plus tx y2. Okay, then what happen is here we write c conjugate tx y1 plus tx y2. Okay, then what happen is here x c t star y1. Okay, and here x t star y2. Okay, then what happen is here x c t star y1 plus t star y2. Okay, then what we get, since x is arbitrary, I write it here, since x be arbitrary. Okay, so what we get here, we write x t star cy1 plus y2 equal to x c t star y1 plus t star y2. Okay, then what we write now, also write here, that means if we this one we write this one, then not a problem at all. Okay, That means t star c y1 plus y2 equal to c t star y1 plus t star y2. Okay, if how we get this one here minus this one, then this one equal to 0, then x0, then this one equal to 0. Understood? Then this one equal to this one. Not a problem at all. So we also see that t star be linear. Okay, so now it is that portion and going to further discussion of that. Finally we need to show that t star be unique. Okay, so it is that portion and going to further discussion of that. We write it here. Finally we show that what t star is unique. Okay, now we write here, suppose that okay, suppose that u v to v is linear, okay, and it satisfies, and that it satisfies here txy equal to here xuy. Understood? For all xy belongs to v. Okay, then what happened? Then x t star y equal to x uy. Okay, for all xy belongs to v. Okay, then so what happened here? This one x t star y difference x uy equal to 0. This implies x t star y difference uy equal to 0 equal to x0. This implies t star y difference uy equal to 0. This implies t star y equal to uy. Understood? This implies t star equal to u. Okay, so we do this one. Now we write here, that means the linear operator t star, the linear operator t star is called the adjoint of the operator, t. Okay, understood? Not a problem at all. So we also discuss this one easily. Okay, that means which one is adjoint and how this one is we handle. Okay, we discuss in this class. We first discuss one linear transformations, obviously give some value, and this value is equal to some inner product, and then we also discuss how this adjoint of some linear operator occur. Okay, and this one be linear. So today I stop here. If you get this type of video, please subscribe my channel. Please see this video regularly, and if you want to give like, please click on like options. If you have any question, comment, suggestions, write it in comment box. So today I stop here. Thank you.